starts. Okay. Okay. Oh, and it's working. It's working. All right, so I did succeed last time in completing a video, and I posted it on the MIE100 YouTube channel. The reason I use that is because the U of T stream and media player, whatever it is, never seems to work really well. So it's a lot easier for me to do it on YouTube, and it's pretty easy for you to access. Lecture 3. What happens when a particle is traveling along a curved path? And also, how do you describe the position, velocity, and acceleration of these paths? So, starting out, we already have defined rectangular coordinates. That is, we have an r vector, and that's equal to x, I, y, j, plus z, k. If you want, you can rewrite that in terms of components of r, but it ends up being the same thing. So what's really important here is recognizing the use of these unit vectors, I, j, and k, I, j, and k. However you want to define everything else, it's up to you. What is also important is that the position vector is also going to be defined by the position vector divided by its magnitude. So essentially that's unity, 1, and if you do that, you end up with this expression here. So I have position from that. If I have position, I can then take the derivative and do the same thing. And I want to describe it. Normally, when I'm writing it at this point, I'm writing it in 3 dimensions. That is x, y, and z components. But in reality, I'm only really going to look at these two throughout most of the course. So vx, vy. I started to introduce a slightly new notation, that is the dot notation. So x dot in the I direction, y dot in the j direction, z dot in the k direction. And all that is ddt of z, ddt of y, and ddt of x. If I want the magnitude, the speed, then what I'm going to do is I'll take the squared sum square rooted, vx squared, vy squared, vz squared, square rooted. And my unit vector will be that expression. So it's the same as the r expression, or the unit vector for the r direction, except that it's with respect to the velocities, vx, vy, vz, v. Same thing with the acceleration, which is a vector. I take the derivative with respect to time of velocity, and then when I do that, I get ax in the I direction, ay in the j direction, az in the k direction. I can also write this using this dot notation as x double dot in the I direction, y double dot in the j direction, and z double dot in the k direction. And you can do the same thing as you did with the velocities. Define a unit vector for A that goes as ax in the I direction, ay in the j direction, az in the k direction over the magnitude of acceleration A. And A magnitude is just going to be that. So let's think about what's happening with a particle that's sort of moving with curvilinear displacement. So again, we're dealing with kinematics. Kinematics is just the geometry of the motion, not the forces causing the motion. So when you look at this chapter, you're looking at motion that's occurring. You're not worried about how it's being caused. So what I want to be able to do is define that position, velocity, and acceleration, excuse me. As a vector, which means I want to have position and direction simultaneously. Which means I may have to come up with a slightly new thing when I'm dealing with an origin over here and a curved path motion. So I have that yellow sphere or yellow ball on the screen. It's traveling from, say, the bottom over here to the top over there. And so at time 1, it's at this position, and at time 2, it might be at this position. So this is its position. Its displacement is going to be delta r. So delta r is just going to be the change in position from time 1 to time 2. Now you can see that that's not a really good description of the path, but it gets to be a really good description if I use smaller and smaller sort of displacements and times. So the displacement is just delta r. And delta r is just going to be r prime minus r. But remember, these are vectors, so there's a lot of information in there. As delta r gets smaller and smaller, it's going to start approaching dr. That is, it's going to approach the tangent to the curve. And you'll notice this expertly drawn diagram that now I have r, and that v is acting tangentially to the path that's described. So since dr if dr is going to be tangent to the curve, and velocity is just dr over dt has no direction, then dr and v both are tangent to the curve. So, to avoid having me handwrite some of this and make it a little bit easier to read, we have the average velocity, or the average velocity, which is just delta r over delta t over some gross or coarse step. If I go to the limit as delta t approaches 0, very, very small, I start to approach dr dt. And if I want the average displacement, I look at the displacement of the particle over time. And its speed is then going to be limit delta t over, as it approaches 0, delta s over delta t, or again, a derivative ds dt. So it's really important to keep those definite 1, 2.
Sorry, ST is just like distance.
Just the distance along the curve. I'll just, 1 second, I'll get back to you. So ST would be sort of defined as this. And it would be the magnitude of that distance, not the direction. Go ahead.
So what is O? Is it the mass?
Sorry, O is the origin. So I'm going to define a new origin here, and that's going to be with respect to.
You can define our origin anywhere you want to.
You can. So if you're doing it, generally there's good ways to do it and there are bad ways to do it. And so, for example, if you have circular motion, you want to be at the center of the circle. If you have some sort of curve motion, you also don't want to be describing a distance in kilometers that's displacing in meters. So again, it's going to be sort of dependent on the problem. So I talked briefly about this yesterday. We don't spend a lot of time talking about hodographs. We should spend a whole bunch more time talking about hodographs. It's a curve described by the moving extremity of a line, the other end of which is fixed, the line being constantly parallel to the direction of motion and having its length constantly proportional to the velocity of a point moving in any path used in investigations respecting central forces. So, what does that mean? If I look at these plots, actually I'm going to sort of skip that right there. I'm just going to focus in on this. I have V and V prime. Now, one of the things that I told you yesterday was that accelerations are not tangential to the path. You may have one-dimensional motion. That's the only case where you might have it and it works really well. But what are they tangential to? So if I have two velocity vectors, or a bunch of velocity vectors, say, for example, along here like that, I can take each of those velocity vectors and create a hodograph. And the hodograph, I'm just going to take the tail of each of the vectors, align them, and then I will create a curve, that yellow curve that you see. That yellow curve is the description of the acceleration as a function of time. If this is velocity as a function of time. But it is tangential to that curve, which has absolutely nothing to do with the physical path that you're taking. So always be very careful with sort of doing that. So all I did, I took those two green lines and I made this graph or figure. Go ahead.
Because velocity is tangential to the path, are they all going to intersect at like point as it's drawn this way?
I'm sorry?
It doesn't, like with the velocities, would they all intersect at a singular point? Like
So I have forced them to intersect at that point. So I take all of the values that I have along the curve. So I've taken all of these. So this point right here and this point right here, and then I aligned all of the tails.
like a translation.
That's right. Once I've done that, then I know what the curve, the hodograph looks like for the acceleration vector. And the tangential to that yellow line at the bottom, is what I look at. So it's very different than the physical path. And that's why you have to be very, very careful when you're doing these, because there's a temptation often to just say, hey, I've got the velocity, the acceleration must follow the same one. It doesn't. It can go in the opposite sense, it can go up, it can go down. It just depends on the situation. As a reminder, and you're not expected, just in case you're wondering, you're not expected to draw hodographs. What you are expected to know, and what is important, is that they're not tangential. Acceleration is not tangential to the path. Everything else will be fine.
The acceleration be the same throughout the whole curve?
No. In that case, remember that acceleration is a vector quantity, and as soon as the magnitude or direction changes, then it changed. So if you, even on these three cases, you can see, even if the magnitude were exactly the same at all 3 points, the direction has changed. Which kind of leads to the next sort of point. Oh, yeah. I think I'm going to try this first. So we have right now sort of these plots right here. And say, for example, this line describes the motion. And if the line describes the motion, we already went through the exercise of doing the chain rule and saying, well, we have dx dt, di dt, dy dt, and dj dt, and recognizing that the magnitude of I and j do not change. So for example, as you look at that curve and as you look at that path, the unit vectors I and j do not change direction. So unit vectors can change direction dependent on the coordinate system that you use. But in this coordinate system, they don't, which makes things a little bit easier. And in those cases, I can ignore the time rate of change of the unit vector, which is superb. And so I get these sorts of equations that I work from. And you'll notice that we're going to start to look at a class of problems where the acceleration is only occurring vertically. That is, if I throw the pen up in the air and I let it drop, or throw it in that direction, it will travel with a constant velocity because there's no air resistance in dynamics, but in the x direction, but it will fall with a rate of g in the y direction. And if I figure out how to do it, there's a really nice experiment that was done on the moon and I will try and share that. That leads into the obvious question is what happens if my unit vectors don't stay in a constant direction? So you can see, for example, here on this figure, you have I and j at various locations. Now, there are other types of coordinate systems I might want to define. And one here is one that is tangential to the curve or the path of motion. So this is something you might see with a projectile. And so with a projectile, you'll have E sub t, the tangential direction, which is going to go up. This still has a magnitude of 1. And this still has a magnitude of 1. However, despite that, it has a change in direction. So when I'm solving for a problem that will have a tangential unit vector, and I'm going to have to define another one, it's going to be the normal component. I'm going to have one that changes direction. So clearly, I'm going to have to worry about calculating derivatives there. So if my unit vectors don't change direction, then my derivatives with respect to time are 0. If my unit vectors do change direction, then they do have a derivative with respect to time. So let's consider this case. I have two vectors, a of t and a of t plus delta t, and they're separated by a distance or of delta theta. There you've got a separation. E sub a is shown, and it describes the direction. E sub a at this time also shows the direction, and it's acting in a completely new direction. So if I have a dot, it becomes d dt of E, A is a function of time, EA as a function of time. And like last time, I can write out everything in the same sort of format. So I take the derivative of A with respect to time and the derivative of the unit vector E sub A with respect to time right here. So I have both of those, and I have to deal with them in the chain rule. And my expression now becomes A dot E in the AT, or A E A dot as a function of time. And that's where my headache starts. So what we're doing is we're going from the first, more simple coordinate system, one that is sort of intuitively something you've probably done a lot with, Cartesian. And we're going to start looking at two other ones, normal and tangential. So I'll have two things that I have to worry about. First of all, the time rate of change of magnitude of A, so that's A dot. And then the time rate of change of direction of A. Go ahead.
Sorry, before, is it usually the change is usually expressed by delta theta, like an angle, or can it be expressed by delta vector?
Exactly. It can be any sorts of terms. In this case, I just wanted to show the difference between the two, and I wanted to highlight that difference with the theta. That's the easiest way, just lining up the tails. So here's my problem. I could consider the simple case, the simpler case, which is motion around a circle. I have a particle, it's traveling along the red circular path. Delta theta is shown here, just sort of the displacement, and that's going to be the basis of one of my coordinate systems, the r theta, which is the last coordinate system we introduced. And r, which is the distance from the origin to point A. So in this case, it'll be constant. Excuse me, xy is the coordinate system of interest here. And I can say, excuse me, because it's a unit vector, E sub A can be described as cos theta plus sine theta in the I and j directions, respectively. Well, in that case, so if I take the time rate of change of that, I end up with EA dot minus sine theta in the I direction, cos theta in the j direction, and theta dot. And what I get from that is that EA is perpendicular to EA dot t. And that's going to be the important relationship in terms of looking at these unit vectors. So I will come up with a number of unit vectors, similar type of approach, and in all of those cases, I will have two that are perpendicular to each other. So just like xy, but xy, it doesn't change direction, EA does change direction. So EA is just E sub A here, and I want to break it up into EAX and EAY. And by doing that, and using the theta that I have, and recognizing that this is unity, so I would multiply this by 1, that's why it's not there, I end up with EA as cos theta I and sine theta j. It's a position vector. It's always going to be a position vector. It's always going to describe what's happening. So I can use it with velocity, and if I have a velocity field in this, I could describe it the same way. But it describes direction. That's all it does. It's really important to solving this.
Does the orthogonal relation only exist in the time where E of A is independent of T? Because as you can see on the board, E of A of T is sine theta times I plus sine theta times J, which is independent of T unless theta is a function of T.
So this is the very simplest sort of relationship, and it's the easiest one for me to show. I can also do this with, and I'll show another derivation later, where we just follow along and look at very small displacements. And when you look at very small displacements, the delta R, that term that goes between the two vectors, does also show to be itself to be 1. But this is the nice way to show it. The not so nice way is the way I'll show it later. What happens here is I can start to also describe sort of angular velocity. This won't be as important right now. It will be much more important later on. And that angular velocity is that term theta dot, or it could also be referred to as omega A. So that's not a W, but a Greek letter omega. So if I take the cross product of omega with the direction vector, it will also be parallel to E sub A, and this gets more useful again in chapter 5. And that's really all I want to say about it right now. One of the things that you really have to remember for later, and we're kind of driving towards a more complex kind of motion. You can see that the first part of this course, we're going to talk about particles. And particles have that unique property that we only care about their mass. We don't care about their size. Well, clearly, the second half of the course, we're going to look at mass and size of objects. And so we'll look at rigid bodies. So this starts to be more important because particles can't rotate because they have no size. Rigid bodies can rotate because they have size. And so you can have a plate that sort of rotates like this. And so that becomes more important in the second half. Now, I haven't defined the second coordinate direction yet, so I'm just going to refer to this derivative as EA norm. So it's acting in the normal direction. And First, I have the change of magnitude. And then the change of direction. When I start to go to the next coordinate systems, so those are nt and r theta, this becomes much more important. So in those cases, I'm going to have to worry about not only the change in magnitude of the quantity of interest, velocity, position, whatever, but also the change in direction. Any questions on this one so far?
On the previous one where you talked about angular velocity,
Yeah.
on the second line, could you go back? Do you mean to write the angular velocity cross? Yeah.
Yeah, that's what I meant to write.
Thank you.
The same part I just missed what was K.
I'm sorry, I didn't hear you.
In the same part I just missed what K was.
Oh, K is a direction. So remember, whoomp, whoomp, whoa, lecture 2, particle motion. No, Cartesian. Ah, yeah, yeah. So in the last lecture, if I can finally do this, there we go. I had defined the 3 coordinate directions. So typically in this course, I only worry about what's happening in the xy plane. But K acts in the z direction. Okay, so a typical problem we might deal with where we start first of all to break down into a Cartesian coordinate system is something like this. Again, expertly drawn stick figure showing you a kid throwing a newspaper. And the kid is trying to hit between points B and point C on the house. And you're given a number of dimensions here. Those dimensions include the step height, 0.2 meters, 0.2 meters, 0.2 meters. The height of the throw, 1.2 meters. The distance that describes point B to the kid, 2.1 meters. The horizontal extent of the steps, which is 0.4 meters. And the distance from the top of the steps to point C, which is another 1 meter. So you have a lot of stuff to sort of keep track of. So you're asked, while delivering a newspaper, a kid throws a newspaper with a horizontal velocity v sub naught. Determine the range of values of v sub naught if the newspaper is to land between points B and C. Kid throws it and ends up on your steps. So you can see this light blue line. You're going to get used to that light blue line because the parabolic profile is going to be the typical sort of motion of a particle or a projectile. So the projectile in this case is the newspaper, and it will go with a constant velocity in x and a decreasing sort of height and a decreasing velocity in y, negative. So if I'm looking at the kid, if I'm looking at the kid, the kid has to hit either point B or point C. And the projectile path is going to be defined by that light blue line. The distance is 2.1 meters. And 2.1 meters plus 1.5 meters, 3.5 meters. So I have two x dimensions that describe how far the kid has to throw that newspaper in order for it to hit the steps. So in order to hit position B, I know, first of all, the kid is throwing with a horizontal throw, which means there's no vertical velocity associated with the newspaper. It doesn't rise or fall as the kid is sending it off. It's going straight. So y sub b is going to be 1.2 meters minus 0.2 meters. So the newspaper has to fall 1 meter in that time. Switch colors. So y sub b is going to equal 0 because I'm going to assume the kid is starting at the origin, which I've defined there, sort of. That's my origin. Plus 0 times time, because I can say it's y naught plus vy naught t plus 1/2 gt squared. And I had a question yesterday about what to do with g. I like to write it as a positive number generally, because, or a positive variable, and then afterwards take care of it. So, if I do that, I know this is 1. These things have gone away. This is the only thing I don't know. I know g. So, if I subtract everything off, I can say, oops, look at that. T sub b equals 2yb over g. Now, if I'm using negative g, then the particle has actually dropped, the newspaper has dropped a distance of 1 meter, so it's negative 1. So under the square root, this won't be imaginary, it's 2 times negative 1 over 9.81. Over negative 9.81, so it's positive. Which will end up with a time of 0.45 seconds. There we go. And I probably should write that. Y sub b equals minus 1 meter. G equals minus 9.81 meters per second squared. Everything depends on how you define the origin. All right. Y sub b is done. X sub b is also going to be x naught plus vx naught times time plus 1/2 acceleration of x in the time direction. I'm just going to use a thick black line. This is 0 because there's no acceleration in x. There's nothing to decelerate in dynamics. There's nothing to accelerate in the x direction. Again, the way I've defined this problem, my origin is 0. And maybe, to make this a little bit better, x and 1. So So I know what the time is because the time for it to hit point B is the same time as it takes to drop to point B. So that becomes time B. And so V naught x naught equals xb divided by t, which equals, in this case, 4.65 meters per second. So, in essence, if I'm looking at the same steps, the kid has thrown to the edge of the first step. Now, I can do the same thing for point C. And that is y sub c is equal to 1/2 GTC squared. X sub c is equal to V naught x TC. No square there. Now, the other thing I'm not doing in all of this, which I really should be doing, is writing units. But that's meters per second, that's meters, that's seconds. That works really well. Over there, it's meters over seconds squared. The meters cancel out, and the second squared is under the square root, which means I get a second. So again, I'm sort of messing around a little bit, but as much as possible, try and write your units down. So y sub c is equal to, how did I define it? 1.2 meters minus 0.6 meters. It's at the very top of the steps, and because it's at the very top of the steps, it's 0.6 meters away, so it ends up being 0.6 meters. X sub c equals V naught x sub t, which yields t, I hit it, V naught x sub c equals xc over t, which ends up being 10 meters per second to enough significant figures that it doesn't matter. It ends up being, the number ends up being 10.0072 meters per second. But as you're solving these problems, you always kind of, two significant digits are going to be enough to describe what's happening. The important thing here is just the idea. One, you can break down a problem. We've gone from one-dimensional motion, that something goes left and right, up or down, to one that can go left, right, up, down at the same time. And by keeping and breaking it up in terms of coordinate systems, x and y, I have a simpler way of describing it. Next week, we are going to talk about projectile motion, and I'm trying to keep you here for the minute and a half that's left. Projectile motion and the other two coordinate systems. So by the end of next week, I won't have to keep making up flubbed questions without talking about real unit vectors and things. Then afterwards, we talk about relative velocity and absolute dependent velocity, and this is a great place to stop. Thank you very much.
Would you mind explain this a little bit? I don't know why this term does not have any direction.
Oh, because I haven't really defined it yet. So if I were to define it, it would be this term right here.
Yeah.
But I
So-
haven't defined it yet, and I don't want to define it today.
Oh,
But next week I'm
so
going
it
to
actually
define
has
it.
direction.
That's right.
And this n means normal, is it?
That's right. So in this case, it's a perfect example of a normal tangential system.
Got it. Would you mind explain this a little bit? I don't know what's the
So
point.
in this particular case, I can either use mine or yours.